Seuraavaksi minulla on ilo toivottaa lavalle uudet professorimme, tai ainakin 2 heistä, jotka esittäytyvät teille lyhyesti teemana My Science. It is my pleasure to introduce our next speaker, Dario Gasbarra. Professor Dario is an applied mathematician with a deep expertise in probability and statistics. His academic journey began in Italy and later continued in Oulu in Finland, where he completed his doctoral degree. Before University of Vaasa, Dario has been teaching stochastics at the University of Helsinki. Currently, he is focusing on 2 fascinating areas: the theory of large random matrices and modeling analyzing data from novel diffusion MRI imaging. At least for me, these topics sound a bit heavier than your average bedtime reading, but I am sure Dario has a way of making these topics more approachable. So, without further ado, let's hear more about the expert himself. Please, Dario.
Kiitos, Jonni. On suuri kunnia olla täällä teidän edessä. So my research topic, I want to speak about a research question I'm working on since 3 or 4 weeks. So the question is, are the axons kissing or crossing? So this is related to signal processing of diffusion MRI data. As you may know, MRI, magnetic resonance imaging, is one of the big success story of science and technology of the 20th century. It's really an amazing thing that we can measure using this magnetic field, what is in our heads. Okay, so what are axons? You know that we call brain cells are neurons, and axons are the connections between neurons. And an axon can be like few micron, as a diameter of few micron, but it can have a length of millimeters, or even there could be even longer axons. So the question is, so if you imagine my arms are axons, are the axons crossing like this, or they are kissing like this, like 2 cars are kissing, they touch? Yes, and this is an important question because you want to, if you can measure this from magnetic resonance, then this tells you something about the connectivity inside our brains. So now, so this diffusion MRI is really an amazing technology. I'm only working with the signal processing aspects of it. So I can describe it like this, using, so imagine, so diffusion magnetic resonance imaging has a spatial resolution on about 2 millimeters, so it can be less. And in 2 millimeters, you imagine a small cube of 2 millimeter side. You have a huge population of neurons, 500,000 or more. And what we are measuring is how the water molecules are diffusing inside these axons and neurons, and also when they, of course, water is everywhere, how it is diffusing also between and within these brain cells. So what we can measure using magnetic resonance imaging is the displacement of these water molecules when they diffuse due to thermal agitation. And so basically each water molecule in this voxel, in this 500,000 of neurons, is sending to us a small signal, but because there are a lot of water molecules, finally these signals can be received by the magnetic resonance coils. By the way, these are the same machine that we have in hospitals to take MRI scan. And in the diffusion MRI modality, what we measure is the distribution of the displacement of water molecules. And so actually, we cannot see these water molecules, and we cannot follow them one by one, but we have some statistical information. And this statistical information is this Fourier transform of the diffusion displacement. So we are talking about microns, and this measurement takes milliseconds. So how, due to thermal agitation, the water is diffusing. And now we can measure this diffusion displacement in several directions, and then we can infer something about how the axons are. So for example, if you have a location, one voxel, where there are two nervous connection crossing, then, okay, the problem is that you will see diffusion in two directions, but then in a short diffusion time, you cannot distinguish crossing from kissing, because, I mean, if you are crossing, each water molecule is trapped in one axon and it can go only one direction. But if there is kissing, you know, the water molecule can move from one arm to one side to the other side of the axon. And now, using a little bit longer diffusion times, we are developing a model to estimate the probability distribution of this displacement. So for the standard diffusion MRI, we have only one displacement, but here we want to take it over longer diffusion time and estimate the joint distribution of several displacement. And this is something a little bit technical, but it's very interesting to do. And this is work in collaboration with my colleague, Professor Sangeeta Kulatinal from the University of Helsinki, and Peter Basser from the National Institute of Health in the US, who is running a big laboratory where he can conduct these MRI experiments. But now I've been speaking too long, so I wish fruitful collaboration between all of us in teaching and research. And thank you for listening.